Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 10, Automated Model Selection for Multiple Regression. So, given the data on a response variable y and k predictor variables, x1 through xk, we want to develop a regression model that predicts the response y. We want this predictive model to fit the data well so that our model assumptions are met and do a pretty good job at predicting new responses, at least the best that can be done. So let's assume that we've got the correct collection of variables, they're measured appropriately, and that our list includes all the possible important effects that there could be. Then in that case, our most general model would include all of those effects, x1 through xk. As we know, the challenge here is if we want a parsimonious explanation of the data that also predicts the response variables well, then we can often remove one or more of the predictor variables from this full model. And so we want to identify which effects are important, the vital few variables that will explain the response in y. All right, so that is our goal. So we're going to study several automated non-hierarchical methods. So these are methods that don't necessarily keep the hierarchy of main effects must be included if higher order effects such as interactions or squared or cubed terms and so on are in the model. So these methods don't necessarily do that, though they can always be programmed to do that. It's mostly a challenge of a human programming the logic of maintaining the hierarchy. So these methods aren't necessarily programmed very well, but they will work. So given a specific criterion, so we've seen several criterions before, such as the AIC, BIC, we could use R squared, things like that. We're going to see several more in this chapter. Given a specific criterion, there will be a best model. And so we want to search the space of models and choose the best one based on a certain criterion. Now, one thing we'll notice is that different criterions will give different best models, and those, right, they may or may not agree. So we may have a few criterions that agree on one model, and then another criterion that chooses a different model. So we want to, in this chapter, learn a principled approach for choosing which criterion to use to choose a model. And if we look at several criteria, how to reconcile the different decisions that each criterion makes. So, before applying these methods, always plot your data, make sure that you've considered the appropriate transformations that may be suggested in the data. Make sure also that you fit the full model and that the model seems to fit well. If not, you can perform transformations or consider a different model, including squared terms or whatever. And make sure that full model at least seems to capture the main features in the data. So different criteria for selecting models lead to different best models, right? Given a collection of candidates from best model, we make a choice of model on the basis of a direct comparison of models, if possible. So if we look at different criteria and we see that there's three models that are the best under three different criteria, I will continue to make that mistake between criteria and criterions. So make a direct comparison of the models if you can. For example, we may find that these three best models all include very similar sets of covariates, but except for one small difference. Maybe one has an extra predictor, one has one too few, but they're all pretty similar. Also, you always want to examine the model adequacy, right? Big focus in this class on checking the assumptions of the model, checking the residuals, influence of unusual observations, and so on. Influence in here is going to possibly be a big deal, because whether certain variables are considered important in a model could depend only on one observation in the data set. And Occam's razor, simplicity. All things being equal, simpler models should be preferred if your goal is to explain the relationship between variables. And always, when you have the context for it, scientific plausibility. Does this resulting model even make sense? If not, think some more about that, and choose different variables, or go back and take different measurements, something like that. Talk to your advisor. All right. So I view the various criteria as a means to generate interesting models for further consideration, without taking any of them literally as being the best model. Okay, science is a progressive enterprise, and we rarely have the correct answer, especially in statistics, where we are making approximations. You should recognize that automated model selection methods should not replace scientific theory when building model. In fact, whenever you've got an actual scientific theory for how a relationship should exist, you should use that relationship. So in engineering or physics, or if you're doing some sort of differential equations, you've got explicit theoretical, physical models that show the relationship between things. And maybe you want to estimate the tensile strength of something, or the friction between two surfaces. And you've got model equations that relate some process, and the unknown is that tensile strength or that friction. And so you should use that actual function rather than this very simple linear regression model structure. You should use the actual scientific model when you've got it, okay? In which case you may end up doing nonlinear least squares or some other model fitting strategy than what we've been doing in class. But there's plenty of methods for doing all that stuff. All right, automated methods are best suited for exploratory analyses when you're not sure what the relationships are, but you want to gain some insight through systematic and procedure and principled strategy, and in situations where researcher has little scientific information as a guide. So we've talked about the AIC and the BIC before. It's based on the likelihood plus a penalty. You want to minimize these. And we've used that for stepwise procedures in a few chapters previous to this one. And we'll be looking at, in those examples, I also included F-tests in an analysis variance table so we could see p-values about whether we would have included or excluded variables based on those hypothesis tests. And we'll look at several more detailed criteria in this chapter. All right. So first, let's talk about different variable selection methods. We've seen backward selection. Forward selection is similar. You're going to start with an empty model and then add variables one at a time until adding one more additional variable doesn't add additional explanatory power. So imagine an initial model, y equals beta naught. That is our starting place for this. Then, if we've got k different variables, one at a time we will add beta 1 times x1, beta 2 times x2, and we'll just add to this model every possible x all by itself as a simple linear regression. And then we'll ask, when we add this variable, is this slope parameter beta 1 different from 0? And we'll find that one of these x's explain the variability the most, and if that one is also significant, then we'll include that variable in the model. So let me scroll down a little bit more. Okay, so let's say that x1 happened to be that variable. Then we will keep x1 as being the most important variable, and then we'll fit every other variable as an additional second variable. So we'll do x1 with x2, x1 with x3, x1 with x4, and so on. And we'll pick the most important variable. And then we'll stop when that additional term no longer becomes significant, meaning that it's not explaining an important amount of variability in the response any longer. So that's basically what that algorithm says. Excuse me. All right. And so you just keep going until you stop. So that's forward selection. Backward selection we've seen before. We start with a full model, and then we ask which variable is least important, conditional and all the other ones being in the model. And then we drop it. And we continue to do that until all the variables are important. And one comment I have in here is about stopping rules. So when we're doing variable selection, we often want to be a little bit liberal. I guess it depends on which direction we're going, or conservative, about whether we include variables or not. So these selection methods should be seen as a way for the computer to get in the ballpark, sort of close to where we, as humans, would have selected a model. So the computer's saving us some effort. But once we get close, then we should make the final decisions by ourselves. For example, we might continue to include variables as long as the p-value is less than 0.5, which is large, right? So we sort of include too many variables, and then do some fine-tooth combed decision making there at the end manually. Similarly, in backward selection, we start with the full model and start dropping variables, but maybe keep variables as long as they are still significant at the 0.1 level, and then we can make the final decisions manually. So stepwise regression, or stepwise selection, is a combination of both forward and backward elimination. Basically, we start at a model. We can start at the empty model, we can start at the full model, or some model in between. We could even start at different places and see whether they all get to the same final model. And the process is we add a variable to the model, as in forward regression, okay? But then at each step we also look to see whether, given that we've included a certain variable, can we then eliminate a variable? Right? Because everything depends on everything else. Maybe you've got variables 1 and 2 in the model. If you include variable 3, maybe variable 1 no longer becomes important. And so you can actually remove variable 1, ending now with a model with variables 2 and 3 in the model. So those sorts of situations can occur in stepwise regression. So one strategy you can consider here is to start, maybe do stepwise regression starting at an empty model, as in forward selection, or as in a full model, as in backward selection, and do the stepwise and see whether you end up in the same place. Do you end up at the same final model? We turn our attention again to the Indian systolic blood pressure example from Chapter 2, in which anthropologists conducted a study to see what the long-term effects are of an environmental change, in particular natives who moved from high altitude down to low altitude, whether that would change the systolic blood pressure of those individuals. And we had 39 Peruvian Indians who were started at a very high altitude in the Andes Mountains, and at some point in their life moved down to a lower altitude in the valley. And we had this list of variables, which is not in a table. Let's see, I think I've got a table of this. If we look at the R code for this example, here is the list of variables, right? We've got the person's age, the years since they migrated, their weight in kilos, their height, and then we have some skin fold measurements for their chin, their forearm, and their calf. We have their resting pulse rate in beats per minute, and then we have their systolic and diastolic blood pressures. So we've got the systolic blood pressure is their response variable, and we also created an additional variable which I called year age. It's the fraction. It's the years since they migrated divided by their age. So it's their proportion of their life that they spent at lower altitude. So, following my earlier advice, we will start by plotting. Oh, there's my table, of course. We'll start by looking at plots. In fact, the first thing I created was a correlation matrix, or at least the correlation between systolic blood pressure and the other variables. And we see that they're all basically positively correlated to varying degrees. Weight has a high correlation. In year age actually has a negative correlation. So the more time you spent at lower altitude, the lower your systolic blood pressure. So I create a bunch of individual plots. So we have systolic blood pressure on the vertical axis, and then we have each of the other variables on the horizontal axis. We have weight, you can see positive relationship here. Height, there's a lot of spread here. Chin, there's a mild positive relationship. Forearm, the skin fold measurements is one person here with really high systolic blood pressure and moderate skin fold measurements. No real strong relationships there. And then a negative relationship here with year age. All right. So let's do each of those forward, backward, and stepwise procedures using either AIC or BIC. So this is largely review for us. So we'll start with forward selection, and I'm just going to jump down to the code. These paragraphs here, step 1, 2, and 3, describe the output, which I'm about to narrate to you. So we're going to start with a linear model with systolic blood pressure tilde 1. 1 here is a placeholder for the intercept. So this is an empty model, right? Just has the grand mean for systolic blood pressure, and we're going to ask, do we gain predictability if we add variables over and above the grand mean? So our stepwise procedure starts with this linear model, which is what I called empty up here. So we start with our empty model. The models that we're going to consider include this form, this formula here. We've got the response variable, and then we've got all of these as predictor variables. So those are all candidates for being included in this model. The direction is forward, and we're going to include the f-test in here. That's fine. That just includes these two columns here in the output table. And K being the log of the number of observations in the data set means that we're doing BIC. So our forward selection model, so I still am using this notation reduced here, though obviously if you start from an empty model and include them, it's not really a reduced model, but I think we understand the idea here is that we're trying to find the better model from some starting place. All right, so our starting BIC value, right? So the stepwise procedure always labels things as AIC, but it's using the appropriate penalty, and so this is actually the BIC value. starting BIC value is 203. That's here. And using forward selection, we find that the best one to add is weight. It decreases the BIC from 203 down to 194. And it also happens to be significant. The next best one would be your age, followed by forearm and pulse and so on. But some of these actually hurt you in terms of the BIC. All right, so given that you've got weight in the model, okay, so here's step 2, where it looks like year age then also becomes important to add to the model. Now, one interesting thing to note, and something that we pointed out back in chapter 2, is that year age actually is not a good predictor. It actually brings the AIC up, which is in the wrong direction, if you include it all by itself. So a model with a grand mean is better than a model with year age. But once you've got weight in the model, then then year age becomes important, bringing the AIC down another about 9 points. Sort of a rule of thumb here is if the AIC decreases by about 3 points, that's a big change. So now we've got a model with weight in year age, and the next best decision is to do nothing. We have the final model. If we were to add chin, the AIC or BIC would go up 2, and everything else goes up even more. So that becomes our final model. If we summarize that final model, this is the same model that we had back in chapter 2, weight and year age. It explains almost half the variability in the response, and that's simply because there's a lot of factors that go into systolic blood pressure, and we actually haven't captured them all here. So let's take a look at doing backward selection. We've seen this output actually exactly before. Here's the linear model. We start with the full model. Okay, so that's our full model. And when we summarize that, we see that weight and year age are significant, but nothing else. So as we know, that isn't necessarily indicative of what the final model should be. We've seen models where nothing was significant, but then variables become significant as you remove other variables. So we'll start with doing backward selection. We're starting with our full model, doing backward selection, and we're using the BIC. And here I've labeled this as doing backward in the linear model object. So the first thing we drop is calf, the calf fold measurement. Then pulse, then forearm, then height, then the chin fold measurement, and then none. And so this is our final model then with weight and year age. So same result as we got with forward selection. Now this example, just because we got the same model forward and backward, is not a rule. This is just one example where that happened to come out true. Often they will result in different models. All right, stepwise selection, just to see, going backwards. And so I actually am starting this stepwise regression somewhat pathologically with an intermediate model that is the exact opposite of the model that we've seen previously chosen. So I'm starting with the variables in here that are all the wrong variables. They're the ones that are dropped. So that is our intermediate model. That's our starting place. This is not a rule. Do not do this as a rule. I'm just showing you how stepwise works. Typically you start maybe with an empty model or a full model and do this. I just want to show the most pathological case where we will end up dropping all 4 of these and end up adding in, let's see, calf, is everything in there? For chin, I should have put chin in here also. But we'll end up dropping everything and then including weight in your age. All right, so we're going to do stepwise procedure, and we've got direction equals both now. And trace equals 0 is going to give me a little bit less output. Rather than show big blocks of results, it's going to just show me in each step all the decisions that were made. So when we output this result, the ANOVA part of it, we see which step we're on, 1, 2, 3, down to 7, and then what decision was made. So we're starting with a particular model, so we're not making any decisions initially. We're starting with this model that has height, forearm, calf, and pulse in it. And its BIC value is 212. And we see the BIC decrease through all this, right? That's our criterion that we're using. In our first choice, we drop pulse, which means, so we've dropped pulse, so now we have a model with only those 3 variables in it, height, forearm, and calf. Then we drop calf, then we add weight, then we add year age, then we subtract height, then we remove forearm, and after all of those decisions, we have a final model, which is systolic blood pressure versus weight and year age. So we got to the same model again. In this data, we have really clear evidence about what the model should be. So they all found the same model. Okay, that's great. I think I'll break here for the second video, and we'll come back and look at other model selection procedures in addition to AIC, BIC, and F statistics.